Hey everyone, welcome to the question show. Your questions, my answers, as always, wherever you are across my channel. If a question pops in your brain, just write it down. I will gather them up and I will answer them here. Now, I record this show live every Monday at 5 p.m. Pacific time. So if you want to get your questions answered and have some follow-ups and chat with the rest of the people watching the show, then that's a great way to do it. But some of the questions are ones from the comments and others are tackled live. So come join us and I'll make sure that there's a link to the next episode somewhere around the YouTube channel. All right, let's get into the questions. Thomas Lucas. If James Webb ever detected a type 1 or type 2 civilization, do you really think that they would ever tell the general public? The government won't even tell the truth about UFOs. So it turns out James Webb is actually the perfect machine to search for type 1 and type 2 civilizations. Actually, and type 3. Type 2 and type 3 civilizations. And just as a reminder, the type 1 civilization is the civilization that's using up all of the energy that falls onto their planet. So imagine you cover planet Earth in solar panels. That's a type 1 civilization. A type 2 is one that is using up all of the energy that's coming from the star. So imagine a Dyson swarm. And a type 3 is using up all of the energy that's coming from their entire galaxy. So imagine every star in an entire galaxy surrounded by Dyson swarms. And the reason that James Webb is really good at catching those kinds of objects is that when you enclose an entire star in a shell of satellites, essentially you're blocking the visible light, but the heat that's still coming out of the star and all of the heat that's getting, all the light is getting absorbed by all these satellites, they then in turn have to radiate their heat out into space. And they would give off a very particular, very peculiar infrared signature, a point source infrared signature that tells you that the energy of a star, but has been shifted into the infrared because it's being surrounded. And James Webb is an infrared telescope. And so it's like the perfect machine to study some kind of Dyson swarm. The other issue, if there was like an entire galaxy, again, the galaxy would give off a signature of infrared, which would be very visible, very obvious. There'd be like a galaxy out there in space. It wasn't visible under normal light, but you point James Webb at it, and now suddenly you've got this object that's the size and the shape of an entire galaxy, and yet it's only giving off infrared because every star has been surrounded by a Dyson swarm. And this is something that astronomers have actually already searched for. Astronomers have done infrared surveys inside the Milky Way looking for Dyson swarms, and they've done surveys extragalactic. They've looked at galaxies around us searching for type 3 civilizations, and they haven't found either. And they've done it well enough that if those existed, we would see them. And so either the possibility is they don't exist, or they're just far away, so rare that we can't see them. And of course, sort of the expectation is that a type 3 civilization would have colonized their entire galaxy. And so it should be very obvious that they're there, and yet no one has seen it. Now, second part of your question, would the government tell us? Well, I mean, the way that James works, and really the way astronomy works in general, is it's not the government who is telling people about what they find. The way astronomy works is you have a telescope, Hubble Space Telescope, James Webb, Ground-Based Observatory, what have you. And there is a steering committee that decides who gets to have telescope time on their telescope. When the appointed time happens, the researchers get to use the telescope. The telescope gathers all this data, dumps it onto a hard drive that the researcher can then access. And what the researchers usually do at that point is they'll come up with some kind of scientific understanding. They will post a version of their paper onto this website called Archive, which is sort of a place, a prepress where astronomers can kind of share their ideas, but it's also very public. I go into Archive all the time and find tons of stories for Universe Today. And they will also submit that paper to journals like Nature or Astrophysics Journal, things like that. And if their paper is really good, kind of groundbreaking, then it'll get published in one of these journals. Now notice the government had no role in any of that. The vast majority of astronomy communication, of discovery, of science work completely bypasses the government. The government, NASA and the European Space Agency, they built the telescope, but they're pretty much hands off in its day-to-day operations and what kind of science is done with it. So if those telescopes were used to find Dyson swarms, type 3 civilizations, it would work exactly the same way, which is that everybody would find out about it simultaneously because the astronomers were the ones who were telling it. And you can see examples of this. Like, remember the discovery of phosphine in the atmosphere of Venus? No government made an announcement on that. It was just the astronomers had done their work. They detected the signal. They went live with what they thought they had, published into journals, published into archive, and the story carried forward from there. So there was not some vast government conspiracy of covering up what astronomers are discovering. It just doesn't work that way. Rid Eco. Sorry it's not directly related to this Q&A, but I can't find the episode where you were asking about how to hide Earth from detection based on what we know about ways we can detect planets. That was Fraser, right? If not, could explain why I can't find it. I didn't do the research, so the research probably came from, or the original video probably came from Cool Worlds. I'm going to guess, and maybe I'll try and find it and link to it. But the gist of this idea is that the Earth is giving off a signature of radio emissions and other things out into space. And there's a certain set of star systems that are perfectly aligned with us. And they could, just in the way that we can detect exoplanets, they're lined up. They could watch the Earth pass in front of the sun from their perspective and know that there's an Earth-sized planet there in the habitable zone, etc. And the solution is to trick them that just as the point that the sun, the Earth, and their distance system is just lining up, we shoot a powerful laser right at them that matches the brightness of the sun so that they don't detect the signal, the dimming of the sun as the Earth passes in front of the sun. And that's a way that we could camouflage our existence to planetary systems or to civilizations that are perfectly lined up. And we know which ones those are. And so we could shoot this big laser every time one of these alignments is happening, but it's very complicated. But yeah, I'll put a link. I'll put some references into this video so you can find out more information. Karlma91. Is it possible to put a satellite into polar orbit around the sun with today's technology? The vast majority of satellites here on Earth are launched into an equatorial orbit. You essentially launch from a place like Florida, you go east, which is kind of like you take advantage of the direction that the Earth is spinning, and that allows you to essentially get an extra 1,000 kilometers per hour of launch velocity. So it allows you to save propellant, or you can launch with additional payload, and it's sort of a nice cost savings for launching your rocket. But one of the downsides is you're stuck with the equator of the Earth. Now, if you want to do a polar orbit, you launch sort of toward the pole, and then you get a chance to see the entire planet Earth. Essentially, the Earth is rotating underneath your spacecraft while your spacecraft is going around and around. Very advantageous. It's more expensive, fuel-wise, to be able to put a satellite into that orbit, but it is better. So could you launch a satellite into a polar orbit around the sun? The answer is yes, and it has been done in the past. So there was a joint mission between NASA and the European Space Agency called Ulysses. And the purpose of Ulysses was to detect the solar wind. And what they did was they sent the mission out to Jupiter, and it did a gravitational assist. But instead of using that as a way to accelerate it out of the solar system, it used it as a way to essentially slingshot around Jupiter and change its orbit, so it was now orbiting in a polar orbit around the sun. And it got pretty far, and it was able to essentially detect the sun from above. The problem is Ulysses didn't have any cameras on board, and so we don't get any pictures of the top of the sun. Now, this is being partly fixed with the European Space Agency's solar orbiter mission. This one does have cameras on board, and it's using multiple flybys of the inner solar system to crank its orbit so that it's going higher and higher and higher, and to start viewing the sun's polar regions. And so it's going to get higher and higher up. It's going to fly above the sun, below the sun, and image parts of the sun that we've never seen before. So it is possible. It requires an enormous amount of energy, because just naturally, as you launch from the Earth, you're getting this 30 kilometers per second speed around the sun, but you get no help in going above the sun. And so you can do a gravitational assist or just a really powerful rocket, but there's not much up there. So there's kind of no reason to go outside of the plane of the ecliptic. Self-worthy. What if dark matter is a self-replicating alien robot army in stealth mode? Good question. I have never heard that as a proposal for dark matter. So what do we know about dark matter? We know that it accounts for about 5 times as much mass as the baryonic matter in the universe. So 5 times as much mass as the regular stuff. So in other words, if it is an alien robot army, then there are 5 times as many alien robots to invade solar systems as there is the rest of the mass in the universe. So that's a thing. We know that dark matter doesn't interact with regular matter in any way except for through its gravity, and also doesn't interact with electromagnetic radiation. And so, again, we talked about with Dyson swarms that anything that produces energy is going to give off heat. And so if that was the case, we would see this enormous halo of infrared radiation from all of these robot probes giving off their waste heat as they did whatever invasions they were planning. So that wouldn't work. The other thing is that we know that dark matter doesn't interact with itself. And once again, if we were looking at these dark matter robots as they were flying around at 5 times as much concentration as a regular mass in the universe, they would be crashing into each other and exploding and causing more heat, unless they were trying to avoid each other. And then they would be using their rockets. Then if they're using their rockets, they'd be giving off waste heat, which would be even brighter. So I think we can categorically assume that dark matter is not alien, self-replicating alien robot army in stealth mode. Michael Purcell. In Astronomy Cast today, you and Dr. Gade discussed iterative design. How might that have worked for James Webb? Right, so Astronomy Cast, this is of course the long-running podcast that I do with Dr. Pamela Gade. We talk about all things astronomy. You should definitely check it out. Go to astronomycast.com, subscribe to it on iTunes, wherever you get your podcasts. And we had a very fascinating conversation today talking about launch delays and what the impacts are to careers and budgets and science and things like that. And one of the solutions that we talked about is this idea of iterative design, that instead of trying to do something really big and ambitious, you break up the problem into smaller issues, improve them one after the other. And when you think about James Webb, there are a bunch of dramatic technological improvements that they had to figure out. I'll give you a couple of examples. The one is the sun shield, this multi-layered extending sun shield that goes out and blocks most of the radiation coming from the sun, helps the telescope cool down almost to the background temperature of the universe. This thing had to fold up like origami, expand outward, and protect the spacecraft. That was complicated. You've got the segmented mirror, each of which has its own little steering mechanism so that all the different parts of the mirror can be angled to within a precision of 12 nanometers to be able to all work as one consistent thing. There's a whole bunch of these technological improvements. And the way you work with an iterative design is you isolate one variable each time and you build a telescope around it. And so you can imagine they could build a telescope with the same mirror size as Hubble, which is incredible, but use a sun shield. And then you could have a fairly small spacecraft that would fit nicely within a rocket fairing, but it would also have its own folding sun shield, and it would be an infrared telescope. You could have, a telescope the size of Hubble, but with a very simple mirror system that you could have them be in individual pieces and you could work this out. So there's a way that you could address every piece of technical risk that you're facing and come up with a solution. And, I've heard astronomers say, like, would you rather have James Webb or 10 Hubbles? And most astronomers would have rather had 10 Hubbles, or 10 Hubbles with interesting iterative developments on top of them that are James Webb-esque. Like James Webb was an enormous risk, enormous cost. It's going to be able to provide views to the universe that nothing else could. 10 Hubbles could not equal 1 James Webb in some of the kinds of discoveries that Webb is going to be able to make. And that's just always the cost benefit that you have. So when you take a big risk, a big gamble, sometimes it pays off, sometimes it doesn't, but it's always going to be expensive. And that's what James Webb was. It's paid off. We're about to reap the boon of science from it, but it cost $10 billion and it took much longer than anyone was expecting. So you can always use iterative development in any project that you're working on. Tau SETI. Hey Fraser, how likely are planets around red giants like Betelgeuse? Probably not very likely. Betelgeuse is actually a very young star. It's only a couple of million years old. It has an enormous amount of hydrogen formed in some giant stellar nebula out there. And in any stellar nebula, wherever you see them, as soon as the nebula starts to form, you get these large pockets of gas coming together and making these supergiant stars. And then these supergiant stars live very short lives, just a few million years, and then they detonate a supernova. They seed the rest of the nebula with heavier elements, but also their shock waves trigger other parts of the nebula to collapse down, leading to other parts of star formation. So supergiant stars like Betelgeuse, their job is to die early and begin the process of life for the other stars like our sun. So there's not a lot of time. In theory, you would get a giant accretion nebula around Betelgeuse as it was forming. And in fact, astronomers have found evidence of even giant stars having accretion disks around them where planets are forming, but they would have to move quick. And you're in a really hostile environment around Betelgeuse. And then just a few million years after your planet forms, your star explodes, and that's that. So it wouldn't be the best place to have a planet, but there could have been planets, there could be planets there right now, but it's a pretty nasty environment to be around. Samreg Surdna. Can we replenish Mars' atmosphere faster than the sun's wind can erode it? This way we don't have to worry about a magnetic field. The way you replenish the atmosphere on Mars faster than the sun can erode it is you stop the sun's solar wind from impacting Mars. And that if you could just block the solar wind, then volcanic gases would seep out of Mars naturally and would thicken in the atmosphere. It would warm up the atmosphere. You would get to the point on Mars where the carbon dioxide would stay sublimated, gaseous form. The water ice that's in the poles would start to melt. You'd thicken the atmosphere some more, and it would actually get surprisingly better. All you would have to do is block that solar wind. And that's tricky. One idea to do that is that you put some kind of giant magnetic bubble at the Mars-Sun L1 Lagrange point. And that's, of course, a spot that's right in between Mars and the sun, and you could block the solar wind, redirect it around Mars, sort of like have cast a solar wind shadow where the material is flowing around Mars but not actually impacting it, and then it would naturally thicken up. So we wouldn't even have to do anything. The trick, of course, is building a giant thing that's capable of blocking the solar wind, maintaining it at the L1 Lagrange point long enough for the time it would take for Mars to naturally recover some atmosphere. Wouldn't be perfect. Mars would still suck, but it would be better. Harrison Stewart. If we were to go to another star system, wouldn't it be more likely that we would live on the moon of a gas giant like a hot Jupiter's that we keep discovering close to the star instead of a planet? You want to live on Endor. Now, we wouldn't want to live on a hot Jupiter. Those things are hot. Like, they are thousands of degrees on their surface, and any moons that are orbiting around them are also going to be thousands of degrees. They're going to be terrible. But if you had a Jupiter-sized planet orbiting at the distance of the Earth or in the habitable zone of its star, and it had terrestrial planets, very large, rocky moons orbiting around it that had tidal interactions, then theoretically you would have a place that's habitable. They would need to have a really good magnetosphere because, as we see from Jupiter, you can get really bad radiation belts around the planet that would be impacting the planet all the time, and you would need to be protected from that radiation, not to mention the cosmic radiation, like radiation. But if you could have all that, then it's perfectly reasonable for the moon of a gas giant to be habitable. The question is, like, is it more likely? I don't think so. I mean, a planet like the Earth is nice, and a habitable world orbiting around a gas giant would be nice. Either one would be like an oasis to find, and I don't think we would be that picky. So we would take anything that is habitable. TJ Zamboni Schwartz. So now the Webb is fully deployed, what is the likelihood that something might go wrong in the alignment or calibration process? I've realized that I've spent the last 25 years bracing myself for its failure. We're almost across the finish line now. All of the major parts of Webb have deployed nicely. The sunshade is out. The secondary mirror has deployed. The radiator is deployed. The primary mirror has folded out. All of the mechanisms, the latches for all the different segmented mirror portions are working properly, and they're able to move the segments around. So now comes the work of fine-tuning the mirror segments so that they're within that tolerance. I said 12 nanometers, where the whole thing acts like a single primary mirror. I can't, at this point, imagine what could go wrong. But I mean, we see with spaceflight all the time. Things go wrong all the time. So stay tuned. But I think you can breathe now. Okay? Just breathe. We did it. We're in the home stretch. More questions in a second, but first I'd like to thank our patrons. Gerald Fay, Jake Carnegie, Wayne Boyd, Jeffrey Schultz, Dave Osborne, Aaron, Jeremy Harris, and the rest of our 819 patrons for their generous support. Want our videos early with no ads? Join our community at patreon.com/universetoday. Greg Miller, is there a point at which light redshifts into nothingness? What are the limits of James Webb as far as how far into the spectrum that it can go? So James Webb is an infrared telescope, and the reason infrared was chosen was that the farther you look out into space, the faster things are moving away from us, and the more the light has been redshifted. And the effect of redshifting light, radiation, is that you take something that was once visible, like say maybe something that was right in the middle of the visible spectrum, and you shift it to the red. Things that were just red light shift into the infrared. Things that were in the infrared are shifted into the microwave. Things in the microwave are shifted into the radio spectrum, and so on and so forth. And eventually, given long enough time, you would have gamma radiation that would shift all the way to the other side of the spectrum and into the radio spectrum. James Webb is designed, it's a mid-infrared telescope, so it's not as sensitive into the infrared as cooled telescopes like Spitzer were, but it still can see stuff that is very, very far away. And it's really targeting at the first galaxy structures forming after the Big Bang. So stuff that is still hundreds of millions of years after the Big Bang. And the farthest that we can see, the farthest that is possible to see, is still in the microwave spectrum. So we haven't even really shifted into the longer radio spectrum yet. In the future, it will, as the universe just continues to expand and galaxies are carried farther and faster away from us. But for now, James Webb is perfectly designed to see what it's designed to see, which is those first galaxies forming together, and they're going to be in this infrared spectrum. GBG5. Since Lagrange points are gravitationally stable places where matter can collect, wouldn't there be a higher likelihood of spacecraft like James Webb orbiting these points to encounter debris? No. 3 of the Lagrange points, L1, L2, and L3, are gravitationally unstable. They are meta-unstable, which means that you can only remain in position as long as you keep using propellant, while L4 and L5, the ones that are ahead and behind in the orbit of a planet, those are stable. In other words, if you get down into the gravity well of those Lagrange points, then you're stuck. You have to use propellant to get out. And I think for a lot of people, we've had this conversation quite a few times, but there was an analogy. I was talking with somebody and they used an analogy, I was just in the YouTube comments, and I thought it was just perfect. Imagine you're surfing and you are riding a wave. You're on the crest of the wave and you're maintaining this position. You're not using any energy. You're not having to work out to be able to ride this wave and come into the shore. But you do have to keep yourself a little bit balanced. And if you balance a little too far in the front, you slip down the wave and it doesn't work out so well for you. You slip too far back and you ride off the back of the wave and you lose that. You have to remain in the wave. And that's what the L1, L2, and L3 are, is these places which are meta unstable. It uses a tiny little bit of fuel to remain in position. James Webb is going to have to fire its thrusters essentially once a month to maintain its position at L2. The second it runs out of propellant, it'll drift, it'll fall out of this zone and drift away. And so no debris is going to be in that region because nothing without propellant can remain there. While L4 and L5, the Trojan areas are filled with asteroids. And so in theory, they could run into something, but it's still very unlikely. They're gigantic spaces. General Angst. Hey Fraser, I'm not sure what benefit a moon or Mars base would have on solving Earth's issues. Are there any? I'm completely over all the Musk stuff. I'm not a fan of the idea of colonizing the moon or Mars, sending 1 million people to Mars to live there, because it's horrible. Mars is it's the worst. And we talk about this all the time. The lack of gravity, the deadly radiation, the lack of breathable atmosphere, the freezing cold temperatures, the fact that there's no capybaras and eucalyptus trees and flying fish and penguins. Like, animals are awesome. Plants, trees, weather, oceans, rivers, forests. Like, these things are important to us, and none of these things exist on Mars. There's just rock, pulverized rock, carbon dioxide atmosphere, sunlight, radiation. Those will be your friends on Mars. But I do think that the moon and Mars are incredibly important places for us to go and research. And so it does make sense to have a base there. An analogy of this is the fact that we have research bases down in Antarctica. Antarctica is a terrible, inhospitable place. Nobody chooses to live in Antarctica. No one goes and moves their family to Antarctica to live because you'll die. It's cold. And yet Antarctica is 1,000 times more habitable than Mars, and then 1,000 times more habitable than the moon. Antarctica is a paradise compared to the moon and Mars. But if you go to the moon, you can build an incredible telescope. It'll allow you to see the universe with a level of precision we've never done before. The regolith on the moon is a historical record of every high energy event that has happened around the solar system for billions of years. You just dig into the regolith, make regolith cores, and learn about all the supernovae and solar flares, everything that's ever happened. The rock on the moon tells us about the formation of the Earth itself. There's a ton of really good, important reasons to set up a research base on the moon. Mars is even better. Again, how did Mars lose its water early and why? What happened? Does it have any volcanism remaining inside of it? Of course, is there any life there, hidden underground? There's a ton of really interesting scientific questions that would be well solved by human beings. Obviously, robots could chip away at these ideas, but human researchers going there would be able to get this work done faster and more efficiently. Apart from a research base on the moon and a research base on Mars with a few dozen astronauts in either, maybe another asteroid with a base on it that will tell us some asteroid secrets, there's really no reason to colonize, to live on those worlds. And anyone who attempts to will be sad, because life will just be struggle and pain for no benefit. That's my opinion. There's a lot of people that disagree with me. They think that Mars is the next frontier and that suffering is worth it, that we need to split humanity into multiple baskets. I understand that argument. I disagree with it. I just think that if we do want to live in space in the long term, we probably want to live in some sort of orbital fashion. I always say gravity wells are for suckers. You were able to make it out of the gravity well of Earth. Why go back down into another gravity well? Let's have a research station at the Earth, Moon, L4, L5 Lagrange points, great big rotating space station. You can dial in all of the things that you want, the temperature, the atmosphere, the gravity, and it's close to Earth and easy to access if you really want to live off-world. But Earth is the best place in the universe that we know of, and definitely the best place in the universe for us. And anywhere else that we go is going to be constant struggle for bare survival. And it's not thriving until our technology trivializes it. So I agree with you. There's no real benefit. Per 310, how far would you need to be under the icy surface, like on a Jupiter moon, to avoid radiation? Do you think windmills in the liquid below or another power source would work for people to live? All right, so how much ice do you need to protect you from radiation? A meter. If you can get a meter of ice between you and space, you're pretty much protected forever from radiation, which isn't a lot. I mean, you could surround your spaceship in a sphere of frozen water and you would be protected. Could you extract energy from below? Sure. Yeah. I mean, in theory, the water is going to be liquid. It's going to be various levels of temperature depending on how far down under the water you go. And the surface is going to be very, very cold. And there's going to be a difference in heat that you could extract energy and use that. I don't know if you'd want to use a windmill. I don't know if there's any currents, but you could somehow use a heat pump to be able to extract energy from the temperature difference. So there would be options, but I think probably people, when the research base on Europa is built, they'll probably just have a nuclear reactor, a fusion reactor. The Einrib. Do photons of light travel forever? Yes. Photons, when they are emitted, will travel forever until they're absorbed. And so when you look out into space and you see the light from a star that is 5,000 light years away from us. The light was emitted by the star. It has traveled all the way through space. It's avoided every single piece of space dust, debris, every other solar system, interstellar object, made its way right into your eyeball and hit the back of your eye, was absorbed by your eye, and you perceived that as light. What an amazing journey. And you can turn your television to just like a static channel. And some percentage of that static that's on your television is actually photons coming from the cosmic microwave background radiation. They've traveled for 13.8 billion years and ended up being detected by your television aerial uninterrupted. So yeah, they'll travel forever. And as long as the universe just keeps going, light will be generated. As long as it doesn't hit anything, it will go forever. Cronus 83. Which would be more efficient, an orbital refueling station or using the moon to refuel for Mars trips? I would say orbital refueling is probably the way to go, but the moon has the propellant there. And so it would be more convenient for you to launch your rocket from Earth, dock with the orbital refueling station in Earth orbit, refill your tanks, and then continue your burn out to Mars or wherever you're planning to go. But you would have to have launched that propellant off the Earth, which is, if Musk is right and Starship gets flying and the costs come down, then the cost might just be a few $1 million to launch a tank of propellant into space. But if you can get it to come from the moon, then you can extract the water from the moon, or hydrogen, your cryogenic fuels, whatever, from the moon, from the regolith, from deposits of water. It would be easier to launch them out of the lower gravity well of the moon and bring it down into Earth orbit, and then have a refueling station. Or maybe you sort of split the difference. You have a nice lunar halo orbit where your spacecraft flies up to and docks and refuels, and then maybe it's out at the Lagrange point and then continues on its journey off to Mars or whatever. I think it's all going to come down to how easy is it going to be to extract propellant off of the moon. If that's hard, and it's probably going to be hard, and it's going to be very expensive to get all of that equipment up onto the moon, for the longest time, it's going to make the most sense to just launch your propellant off of Earth, even though it's going to be very expensive. You're going to have to launch a rocket to launch a tiny little bit of propellant and put it into orbit. But still, water, you just pump it out of the ground and it's easy to turn it into propellant. So I think that in the near term, it'll make the most sense to refuel in orbit. And in the long term, when we finally master it, it'll make more sense to bring your material from the moon. But the best idea, I think, is you bring it from an asteroid that has like no gravity well and could theoretically, or you tame a comet. That would be great. Antonio Norworthy, aside from entanglement, are we aware of any forces or phenomena that propagate instantaneously regardless of distance? Not that I know of. There's various versions of entanglement, and I'm a little outside of my area of expertise. The problem with entanglement, and like people, when they learn about this idea of entanglement, this spooky action at a distance, they think, you can have two particles that are connected to each other in such a way that if one is observed, the other one will fall in line with the observations of the first one. And then as you separate them, this happens instantaneously. So it's not like you have to get this propagation at the speed of light to go from one particle to the other. If one is observed, then the other will be, if one is spin up, the other one will be spin down. But the problem is that you can't actually use that to communicate, because there's no indication. If you observe one of those particles, there's no indication to the people who took the other particle away that that particle had been observed. So you won't know to observe your particle. It's not like it suddenly pops open and goes, the other one's been observed. It's just, it remains unobserved by you. And then you observe it and you're like, we got spin up. That must mean that the people with the other particle got spin down. But no information is being communicated. And so entanglement, even though it's a really cool idea, can't be used to send information. So if we want a way to communicate at faster than the speed of light, we're going to have to discover something new, which so far doesn't exist. Andrew Freihofer, what are your favorite Bortle 1 locations that you have been to? So the Bortle scale, this is a way of classifying the darkness of your sky. I think it goes to like 8, where 8 is horribly light polluted and 1 is completely non-light polluted. And as you move through the scales, it gets more and more. And at 8, you can just see a couple of stars, maybe the bright planets, but you really can't see much. You can't even make out constellations. While, say, with bortle 1, you can see all the way down to stars that are like 6th magnitude with good vision. It's incredible. So the best location that I've ever been to was Australia. I was in Australia back in 2018 to give a talk at a conference, and my wife and I rented a caravan and we did a road trip, and we were in the jungle on the way along the east coast of Australia and very far away from civilization. And the skies are incredible there. Now, I'm sure they get better if you go into like the outback and the air is a lot drier, if you go to Chile and the Atacama Desert, but still, it was absolutely stunning. The thing that's surprising to me is that you lose track of the constellations that you know because all of the stars are so bright. So it's not just like, oh, there's the Southern Cross or there's Orion or whatever. All of the stars are suddenly so much more brighter, and it's hard to find your place in the sky, which was quite surprising. The other thing that's kind of amazing with Australia, and this is more about its position, is that the core of the galaxy is directly overhead. And so I'm so used to being in the northern hemisphere, looking down towards the horizon and just seeing in the summertime the core of the galaxy peek up over the treetops, and then it's gone within a couple of months. But there, it's right overhead. Some of the best stuff to see with the telescope is directly overhead. Plus the planets going right overhead. Amazing. But to sort of take this analogy even further, I talked to an astronaut about, he was an amateur astronomer and went to the space station and wanted to experience being an astronomer, but also being on the space station. And he said it was impossible. As you go into the nighttime on the space station, the sky is so dark that the stars are so bright that he couldn't find his way. He could not recognize anything, any constellations, nothing. And you only have, say, 45 minutes of staring out the window as the space station is flying through the shadow of the Earth before it's in sunlight again. And he was shocked at how he became completely unmoored from navigating by the stars, a thing that he was very expert at, that it's very disorienting, and he found that really tough. So that would be like the finest bortle location possible, and it was terrifying, I think. So I want to try it. Flight level 180. What star are you most excited to see from James Webb? The early stars or something interesting more close by? I mean, James Webb isn't really going to be focusing on stars. I mean, it will. I mean, obviously you can look at stars if it wants, but that's not the targets that are going to be the most interesting. The two main classifications is it's going to be looking at galaxies as far away as possible, right almost to the edge of the observable universe. The first galaxies are forming, very interesting. It's going to also be able to look at exoplanets directly. And the thing that I'm most excited about JWST doing is observing the atmosphere of an exoplanet that is within the habitable zone of its star. So it will be able to essentially sense the chemicals that are in the atmosphere of a planet that is orbiting, say, in the TRAPPIST-1 system. And although it won't be definitive, we will find out some very interesting things. We detect water vapor, then suddenly we know that there's water on these worlds in their atmosphere. Maybe we'll detect some combination of water vapor and oxygen and ozone. Maybe we'll detect chemicals that shouldn't be able to last in the atmosphere of a star, like methane, things like that, that could give us a hint that maybe there's some life there. So the observations that I'm most interested in, I would say specifically when James Webb is pointed at the planets in the TRAPPIST-1 system, that is going to be an outcome that I am really looking forward to, because it could very well tell us more about all of these planets that are in the habitable zone. You've got these 6 planets, some of which are in the habitable zone, some of which are too cold, some of which are too hot. It's like a perfect science experiment to try to figure out how planets work at different ranges from the star. I think the TRAPPIST-1 is the most interesting planetary system that we know of and will be the ideal target for James Webb. So that's what I'm most excited about. All right, those are all the questions that we got this week. Thank you, everyone, for asking your questions in the comments, chat, and then all the people who showed up for the live show and asked your questions and all the follow-ups. Super fun. Have a great time. Again, I do this every Monday at 5 p.m. Pacific time. So if you want to come and join live, you don't get the pretty graphics. You just get me just yakking at you. But still, it's a lot of fun. So come join us for one of the live shows. All right, we'll see you next week. If you want a single comprehensive resource for space news, you'll want to subscribe to my weekly email newsletter. Every Friday, I send out a magazine of space news with dozens of stories, pictures, brief highlights, and links so you can find out more. Go to universetoday.com/newsletter to sign up. It's totally free. And did you know that all of my videos are also available in handy audio podcast format so that you could have the latest episodes as well as special bonus material like interviews with me show up on your audio device? Go to universetoday.com/audio or search for Universe Today on iTunes, Spotify, or wherever you get your podcasts. And I'll put a link in the show notes. Thanks to all the moderators, and a special thanks, as always, to Chad Weber and Nancy Graziano.